technical pause and we'll start.
Hi, good afternoon. Good afternoon. I am gonna tell you a short story. And in order to tell you this story, I first have to bring us on board this idea of motor adaptation, which Lior Shmuelov also talked about. But and the idea of the two components of motor adaptation that again have been brought up here by a number of speakers. And then I'm going to focus in on one of those components, which is the implicit component, and tell you about a little experiment we did where we were trying to see about the possibility of enhancing the retention of the implicit component, of allowing, this is going to be in cerebellar patients, allowing cerebellar patients to have improved implicit retention. And it's going to look hopeful at first, but like a lot of things I think in rehabilitation, it's going to be disappointing in the end. And I'm going to use that to talk about something that Lior touched on also, about the idea of actually leveraging the explicit component, which is where a lot of the field is today. As you know, this is the audience. Hello? I don't know. Why doesn't it play? Maybe. Let's try that. Okay. So I don't want the noise. All right. So movement's complicated, right? This is something I do. I really like it. But you can imagine that this would be hard to study, right? And as a result, we look for things that are a little bit easier to study. And I'm going to go to something that's much easier, which is just making a movement from one position to another position, right? Like that's almost as easy as you can get, although the tapping tasks, I guess, are well, arguably a little bit simpler, right? And in these tasks, just like we already talked about, what we do is we allow people, now I want to go back to pointer mode. We allow people to make the movements, and while they're making the movements, the hand goes one way and the cursor goes another way, and they have to figure out like how to actually move their hand to get the cursor to the target. It's not that complicated. You just move slightly to the right. But you can sort of imagine that if the gap between the hand and the cursor is small, then you don't really notice it. And implicit processes which you're not aware of take over and correct your errors. And if the gap is very large, the cursor goes one way and the hand goes one way and the cursor goes a completely different direction, you notice it and you make corrections on your own, right? And these sort of two processes function together. And what you see is that before we even talk about the two processes, you see this basic pattern that on every movement, if you have an error, you correct that error on the next movement. So I'm going to put this down because it's bothering me. Here we go. So this is a learning curve. This is the direction that people are going over time, right? And they get better, just like we're used to. And then all of a sudden, we turn off the perturbation. So now, all of a sudden, they make an error in the other direction. And what happens is that on the following movement, they correct. And so you can see that one movement's worth of error is enough to drive a correction on the following movement. And that idea led to models which say, oh, maybe we can describe this process as a process of a simple state. There's just like, where do I want to go? And every time I make an error, I fix it. If I moved a little bit to the right, the next time I move a little bit to the left. If I move a little bit left, and so you can you have where I want it to go, which is X. This P is the perturbation. Y is where I actually ended up. I ended up where I wanted to go, plus whatever we did to me. And so next time, I'll take that error, the left or the right. I'll reduce it by a little bit so I don't overcorrect. So instead of correcting for the whole error, I'll correct for maybe 20% of it. And the next time I'll go to the same place, but with a correction, right? And then there's this other term here, which is going to be important, which is that if I don't make any error, if y is 0 and I'm actually hitting the target, then I will slowly forget the perturbation. So there's this a which is less than 1, so that if I move, so I'm moving straight and the cursor goes this way. It's like, oh, that's not good. So now I move here and the cursor's close, right? Oh, and now I move 30 degrees and I hit the target. The next time I won't move to 30 degrees again, I'll move to 27 degrees. And if I still hit the target, next time I'll move to 24. So I have a sort of bias inwards, a forgetting factor, right? And so this is pretty simple process. I learn on the basis of my errors, and I slowly forget back to what seems to me like is supposed to be the baseline. And that describes the process of learning pretty well. Except, the point of studying motor learning, I don't know if you guys know this. I mean, maybe you do. I don't know how much you tend to give talks, given your background, but it's the ability to show cool videos. Right? Like, that's why we went into this field. Uh-oh. There we go. I gotta turn it off again. That did work. Did it work? Or we don't have maybe we don't have a video at all. All right, never mind.
You have to get out of pointer mode.
I'm out of pointer mode.
You're in present mode now. You need to display settings and you can display settings.
Oh my gosh. How did that happen? What do I have to do?
Display settings, the middle option in the top bar.
I'm lost.
Trying.
Yeah.
I think there's get out of pointer mode.
We're out of pointer mode. We're 100% out of pointer mode.
Okay. Okay.
How did that happen? It just seems so wrong. Here we go. I got it.
Okay. Okay, now.
All right. We're not going to worry about the video. All right. So, what the video was supposed to show, what you get to see in the video, which is kind of fun to watch, and they're going to distribute the slides, you can watch it yourself, is a lot of professional basketball players missing their free throws, right? It's really, to watch these like highly overpaid athletes missing free throw after free throw is really fun. But the thing that we're going to take from it is this idea that I already mentioned, that the correction is not just one thing, it's actually two things. There's a implicit correction when you miss by a little bit, and then there's these big mistakes that they make sometimes where they totally miss the target, where they're going to do something explicit, they're going to decide to do something different next time, right? And that idea that these two things are going on led to, a long time ago in 2006, led to the proposal of a two-state model, very, very similar to the model that I just showed you, but supposedly with two things going on, right? And the two things that are going on are a fast state, which where the changes are quick, So I learn quickly and I forget quickly. And a slow state where the changes are slow. I learn slowly, but I retain more, right? I forget more slowly. And you can do this cool thing with this two-state model, which is you can do something which is called spontaneous recovery. And in the spontaneous recovery task, I send the cursor, let's say 30 degrees this way, until you learn. So there it is going 30 degrees this way. And now I'm going this way to get the cursor to go like that. And then I flip it. Okay, so now the cursor is going to go 30 degrees that way. So I'm going here, it'll go over there. Right? All of a sudden, I'll make a 60-degree error. Right? And so, of course, I correct very quickly. And then what I do is I just let you move your hand. I don't show you the cursor anymore. Right? So you've trained, now you're going 30 degrees this way. I stop showing you the cursor. And you sort of wonder, what is your hand going to do? And in the one-state model, you would sort of drift back to zero. But what real people do, and what the two-state model do, is that they actually go past zero. So they're aiming the way they used to. Right? As though they remember the first thing they learned at the expense of the second thing they learned. Right? And this works really well with a fast and a slow state. You can see that here, where the fast state learns quickly and then sort of starts forgetting. The slow state learns slowly. But when I do the counter perturbation, the fast state quickly compensates. The slow state stays close to where it was because it learns slowly. And when I turn off the feedback, the fast state drifts back to zero. The slow state drifts back to zero, but very slowly. And so what you see is a revelation of the slow state underneath the fast state. Does that make sense? Idea? So here's the two-state model, and I'm not going to walk through it, but the basic idea is you've got these same forgetting terms, slow and fast, and learning terms, slow and fast. A slow, A fast for forgetting, B slow, B fast for learning. And that kind of model fits the data pretty well. And one of the things people found is that if you ask people where they're actually aiming, it tracks the fast state pretty well. If you take the difference between where they say they're aiming and where they're actually going, that tracks the slow state pretty well. So you can sort of separate not only in terms of the two time constants, but also in terms of what people know that they're doing. These things match up. And there are other models, and I don't want to talk about them in any depth, but just so you understand that this model I'm selling you is just one of a family of models. And what you're going to find in all those models is that there are two states, because there really are two major time constants in the data. Okay? And that there has to be some interaction of an implicit and explicit. And that the explicit responds more quickly. Right? All those things are sort of build whatever model you want. You're going to have to capture those facts. So here's a two-state model fitting some data. So this is real data from some people. And that it fits also for cerebellar patients, but you can see that they learn more slowly, right? And we had this idea that there were theories out there in the literature. This is a very old experiment, but we're still trying to get it published. Theories out there in the literature about things you could do to make the slow state stronger. You get more of the slow state. And that was exciting because we thought maybe we could then leverage it to help training. Like maybe that way people would remember what you trained, they trained longer. And there were three different sort of ideas out there. And the one that's going to work, so I'm not going to talk about the other ones, is overlearning. So if you train people for longer, they're supposed to have more slow state, which makes sense because the fast state is sort of dying out and the slow state is still growing. So you should get more and more. In fact, right, what you see here is that the overlearning really does produce, right? So this is if they keep practicing for much longer than the other groups, they really do have much more spontaneous recovery, right? Much more slow state built up, apparently. That'd be cool, right? Wouldn't that be awesome? And also exciting for us, I mean, it's a much weaker effect, but in the cerebellar patients too, we got more slow state. So did it really work? Well, we fit the model, right? The same model that I was talking about with the fast and the slow terms. And just to be clear, what we expect to see if you're getting a strengthening of the slow state is that the AS, the slow forgetting, should be less. It's actually AS being bigger, but you should get less slow forgetting and more slow learning. BS should be more. And in the control group, you get exactly that, right? A slow is bigger, meaning that there's more retention, less forgetting. And B slow is smaller, meaning less change. You retain it better. Right? And the fast process hasn't changed. Unfortunately, in the cerebellar group, we didn't get that effect at all. The cerebellar group, you haven't actually influenced how they perform. And just to make sure that what we're seeing, because you don't trust models, that what we're seeing is really there in the data. We made a prediction about the data based on these findings. So if you really are getting more slow learning in the controls and not getting it in the patients, right? Then you should get that in the counter adaptation, you can actually see the learning rate slow down in the controls, whereas in the patients, the actual learning rate, that is how fast they're going from going this way to going that way, right, shouldn't change. And that's really what we saw. Here we have in the control group, you can see that in early adaptation, the overlearning and the standard are at the same pace. Each dot here is a particular person doing the task. And this is their adaptation rate, like how fast they're learning. And they learn more or less at the same rate in the two tests, which makes sense because the two tests are identical in the initial learning. But in the overlearning, they get a much bigger slope in the standard task than they do in the overlearning task. And that's for almost every subject, right? So their learning has slowed down, right, in the counter perturbation. Yeah.
So I thought that in the counter perturbation, you basically affect the test process, right?
Well, both processes are affected, right? But and so you, if you look at this as a percentage of the overall rate of adaptation, it's not huge because people are really changing quite quickly there. But if the slow process has been slowed down, you should see the slope get slower. Okay? But you're right that this is dominated by the fast slope, and yet, right, we do see the slope getting smaller. Whereas in the cerebellar group, we see no such effect. Right? We haven't really affected their ability to retain the slow learning, the implicit learning.
So getting it right, they did not retain, didn't retain.
What you get, so you get, like you guys saw, there is the spontaneous recovery, there is more of the slow state, right? But that's primarily because the control group managed to plateau over the overlearning thing, right? Whereas or even by the standard learning, they've plateaued. Whereas the cerebellar group hasn't plateaued by cerebellar by the end of the standard learning, and they're still going up a little bit, right? And so there's a small difference in the amount of slow learning that they have, and that is what leads to the difference in the spontaneous recovery.
Develop patients when they reach, like, wait until they reach plateau, and then.
Yeah, I mean, should, okay. So that gets the idea that's already been brought up, that maybe the explicit process has more options for being leveraged. And this point that I raised with Lior, that it turns out that cerebellar patients actually can adapt better if they understand better what the task is, which is sort of interesting because supposedly their problem is with the slow and implicit learning. And it connects us to ideas that I want to raise here that I think are important for, this is largely an audience of therapists. I mean, some of us are motor learning people, but a lot of us are therapists. That in our field, we talk about the idea of there being more than one explicit process, right? That the explicit process is not just one thing, which makes sense when you think about it, because in our brain, a bunch of stuff is going on. And to bring that home, I want to say that there are many ways to measure the explicit process, right? And if you want to read about them, go read the thing. But you can imagine, I'm going to give you two that are important. One is the kind of measurement where I tell you what I intend to do. So this would be like, I show you a bunch of numbers, you show me a bunch of numbers, and I say, I'm going to head for number 6, right? Or there's a cursor and I get to play with it until it's where I'm planning to aim. Places where I express, like what's explicit about it, I can explicitly tell you my plan. There's another whole set of measures, so that would be in purple, can be recorded. There's another whole set of measures where what I'm doing is I'm asking you to stop. Right? So please don't use any strategies. Please aim directly for the target and not anywhere else. And those sorts of tests, you can put it under can be controlled. And it turns out that whether we're looking at whether the explicit process can be reported or whether it can be controlled, we can get different results. Right? So without going into what the manipulation is, we can create a situation where one set of subjects has more controlled explicit, and another set of subjects has more reported explicit. Just by how we actually go about training. And one way to explain this is the possibility that there's more than one explicit underlying thing, more than one kind of strategy, more than one kind of aim. And that, then you could say, oh, these different measures sort of measure these two different kinds of aiming separately. Maybe one measure is mostly this and the other measure is mostly that, or the way we've drawn it here, one measure is some, even combination of the two while the other one is weighted. Right? So it doesn't have to be one is one, the other is the other, but something is different about how we're taking those into account. And this lines up, I'm not going to, sorry. I took out the slide because of time. I wanted to be on time. I think I'm going to be okay. But you're missing this really excellent slide from this really excellent paper, and I will put the slide back in before I send the deck to Jason and Chai. showing that there really are two components that you can get. They call it, in the original paper, they call it cached and computed, right? Or cached and rotation. But the idea is that if you have a small enough cognitive load, a small enough number of targets, small enough planning load, you can remember what to do with your hands. There's only 2, 3 things you need to do. You can remember it, right? But if it gets more complicated, you start to have to calculate it. If you have to calculate it, it takes you more time, right? And so one is sort of memory load dependent, and the other one is calculation load dependent. And they show that they can dissociate them. And so one of the questions that's really ripe in the field, I'm telling you about this right now, is can we, I'm leaving this as a question for us for the lab, right? Can we show that the thing that cerebellar patients are good at is one or the other? And can we then use that in some way to help target training? That's it. I want to just thank the advisors I work with, Dagmar and Liad, and the students who worked on this, Thomas and Yana, and you guys for listening. And that's it. All right.
Can I ask you something?
I think. Yeah.
Are you able to do a V sign with your right hand?
What's that?
Are you able to do a V sign? Good. Is this an explicit task, what you've done now, or implicit in your understanding?
I would say, like, I mean, so in this task, the reaching and the thing. Well, I understand. I am answering you. Trust me. In the task that I discussed, explicit and implicit components interacted, right? And I think generally speaking, you want to imagine that in every task, there's some combination of explicit and implicit processes, right? So here, I think that it has explicit and implicit components, just like everything else. Does that help?
What is the explicit? What is the implicit?
So it would depend on how we did it, the way we just did it, right? I was trying to explicitly point my fingers in 2 different directions, right?
Do you
But-
have any idea how this was done?
So this review that I referenced, we go into this in some depth. Actually, these exact questions. There is you can sort of separate things into stuff I can meaningfully talk about, stuff I can meaningfully control, right? And so there's some motor skills that I have some control over, but I can't meaningfully talk about, right? And posture and balance come to mind. Like you can know how to ride a bike, right? And you might have some idea explicitly about what it means to steer, but you have very little idea in terms of what you can describe, what it means to balance on the bike. Right? And you can get things that go the other way too, things that you can easily describe. Sorry, other way too, things that you can easily control, but you have very little option for describing, right? Like, so I don't remember which way I went. Anyway, so these different ways of looking at it, right, will give you different answers in different tasks.
Explicit is not equal to verbalize, be able to verbalize. You can be explicit about something, but maybe you cannot verbalize it well.
That's right. So I would hesitate a little bit, right? So I certainly think that there's an important distinction to be made between I can control whether I'm doing it or not, and I have some ability to understand what I'm doing, which could be to verbalize, but it could also be to conceptualize. Like sometimes I have pretty clear concepts about what I'm doing, but I'm just not very good at, I just don't have the right words, right? And I think that the question of whether I can verbalize or conceptualize it is a little bit tricky. You find, so I teach Aikido and my partner teaches Pilates. And one of the things we talk about is how interesting it is that different metaphors work for different people. So saying something in a way that one person will be able to do it, right? Will understand what you mean and have the concept and be able to do it, may not be the same as the way you want to say it for somebody else, right? But in either case, you know, as you develop your idea to express what you're doing in different words, your concept of what you're actually doing gets richer and richer, right? But that may or may not be related to your ability to decide to do it or not. Yeah.
Regarding the mirror neuron,
Yes.
in a scale between implicit and explicit, where would you put it?
That's you know, that is such an, Roy, where are you? Is he still here? Yeah, you haven't thought about, because I have not thought about that question at all. Seems like a great question.
Can you repeat it again?
So the question is the activity of the mirror, I don't want, mirror neurons is, with apologies to Lee, I want to call it the mirror system, right? Is the action observation system an explicit or an implicit system, right? Is it properly understood as implicit or explicit? It's so it operates implicitly. So I mean, but has anybody, do you know about anybody who's addressed this question in any sort of experimental, theoretical way?
We did some manipulations using mesh suppression from movies. Conscious, unconscious.
I'll tell you one experiment which doesn't quite address that, but still I get to then feel like I've said something. A friend of mine, Daniel Glazer, and I was somewhat involved with these experiments, showed, so they took, a little bit complicated, they took capoeiristas and they had them do capoeira moves. And then they took people who know how to write down dance moves and they asked them to write down what the capoeirista had done. And they showed them to ballerinas, male and female. It was matched. There were male and female performers on both. And they had the dancers perform what the capoeiristas had done. And then they showed these videos to capoeiristas and to dancers. And they saw that when you're watching something that you know how to do, you get much more mirror system activation than when you're watching something that you don't know how to do. And I think in my head, that lines up with Roy's idea that it's automatic. But there is a sort of question in the discussion with Shai about how much of that is conceptualization. And they have a follow-up experiment that they never published, and I don't remember the results, but I can find out for you, where they showed there's things that male dancers do in ballet that female dancers don't, right? And so you can sort of say, okay, they know exactly what it is. They've seen it 1,000 times. To what extent is their actual ability to do it part of having the mirror system activate? And I'm afraid I don't know the answer.
But maybe if they want to learn something, that my nervous system will be more activated. Like if I'm going to Pilates and I want to learn something new, so the automatic system will be more.
Yeah, so I mean, we do a lot of our learning in Aikido by sitting and watching the teacher.
Yeah.
And we train the observation system to train the motor system.